Okay, so let's restart the discussions we were having. Yeah. So, yeah, we were talking about subgroups, right? Okay. So we had introduced three very specific forms. One was what we call the centralizer, one was what we call the normalizer, and one was what we call the center of a group. So let us just quickly recall. Okay. So recall number one. So yeah, so let G be a group. That's quite general in sense. So for any subset, we had defined the centralizer of that subset as, so it's the set of elements in G which commutes with every element in A, right? AX. So this happens for all A in capital A. Number two, we had the normalizer of A. So this was the collection of elements in G such that it commute with the whole set, right? Whole set. And thirdly, we had described the center of G, which was collection of elements in G which commutes with every element in G, right? So this is equal, so this is for all G in G, right? And this is precisely the centralizer of G in G, right? This is quite obvious. Moreover, we can also say something more about the centers is that, or I should say centers or normalizers or centralizers, is that if G is abelian, then the centralizers, the normalizers, the center, they equal the whole group, right? Centralizers and normalizers equal the whole group for any subset, and the center equals the whole group as well. More generally, they form subgroups of G. Okay. Proving normalizer to be a subgroup of G is exactly similar as how we did, how we showed that the centralizer of A is a subset, is a subgroup of G. Showing the center is a subgroup of G is, it's obvious from the fact that it's indeed a certain centralizer. We have shown that centralizers are subgroups of G. The center of G is one such centralizer, so hence it's also a subgroup of G. Okay. A trivial fact is that the centralizer is a subgroup of the center is a subgroup of the centralizer. Centralizer comes as a subgroup of the normalizer, and the normalizer comes as a subgroup of G. So it's quite like this. Let's talk about some examples. Okay, consider the quaternion group. So I guess you know what a quaternion group is. Okay, so these are simply your unit vectors in the three-dimensional plane. Okay, like if you consider the equation of a line as a vector in a three-dimensional plane, then you require three unit vectors, right? They're I cap, j cap, and k cap, and they obey very trivial properties that ij equals to k. Then you have jk equals to I, you have ki equals to j, and if you just alternate their positions, then you get a minus sign. So it works like as a circular loop, like yeah. So ij gives you k, ki gives you j, jk gives you I, and if you reverse the direction, then you get a minus sign. That is ik is minus j. So let me just write it down here. Yeah, so ik is minus j, kj is minus I, ji is minus k, and then these elements when multiplied together they give you 1. So I dot I is 1, j dot j is 1, k dot k is 1. Okay, sorry, I guess it's minus 1. Yeah, I guess it's minus, correct. Okay, so it doesn't exactly seem like like what you have in a three-dimensional plane, because in a three-dimensional plane, if you recall, then you have the dot product of each of the unit vectors, they come out to be 1, right? Dot product of each of the unit vectors, they come out to be 1. So each of these symbols I, j, and k, they somewhat also you know consider the properties of complex numbers, of the imaginary numbers, right? Their squared gives you -1, right? Okay. So it's precisely a non-abelian group. If you observe, it's a non-abelian group. It's a non-abelian group, right? Okay. Clear? So this is the indeed structure of a quaternion group. My question is, if I consider this set, or rather say, if I consider the element I, okay, then what is the centralizer of I in G? Centralizer of a single element, it's typically, suppose A is a singleton set, then the centralizer of A is usually denoted as like simply like this. Okay. So what is the centralizer of I? So if you carefully observe, the only elements which commute with I is ±1 and ±I, nothing else. Right? It's quite obvious. Similarly, if you try out the centralizer of J, then it will be ±1 and ±J. Centralizer of K is ±1 and ±K, right? Okay. Let's consider one more example. Let's consider D8. Okay, let's consider D8. Um, Example 2, D8. So D8 is the set of elements 1 R squared R cubed, SR squared SR cubed, right? Let A be the set 1 R squared R cubed. Now, if you guys know what a cyclic group is, or a cyclic subgroup is, then you will obviously observe that this is a cyclic subgroup generated by R. We are not readily using that notation because we have not yet introduced the concept of a cyclic group. Okay. So our claim is that the centralizer of A in G is A. Okay. So this is the first claim, and the second claim would be that the normalizer of A in G is the whole group D8. Okay, G is D8. G is D8. Okay, let's check whether the claims are true or not. Okay. First thing first, uh, the elements in A are simply powers of R, right? By the rules of exponent, if you choose an element to be a power of a certain element, that if you choose an element to be of this form, then every power of A will commute with this, right? So every power of R will commute with every element in A, precisely. Therefore, A should be a subset of centralizer of A. That's quite obvious. That is, A is a subset of the centralizer of A in G, right? So the only thing we need to check is that whether there is any other element which commutes with A or not in D8. Let's see. Will S be in D8? Will S be in D8? S will obviously not be in, sorry, will S be in the centralizer of A? That is, will S commute with these elements? Obviously not, right? Because if you consider the generating structure of D8, then you will observe that SR is, sorry, I will write that RS is SR inverse. So R doesn't commute with S, or I should say S doesn't commute with R. R is an element of A, so S clearly is not in the centralizer. Now, if S is not in the centralizer, then clearly SRI, these sort of elements are not in the centralizer, right? For any I. It's clear, right? Because if so, if SRI elements, these form of elements are in centralizer, then R to the power minus I is also in the centralizer. It's quite obvious because of the structure of A. But then if you compose them by the closure property, so SRI times R minus I, this will give you S, then S becomes in the centralizer, but that's a contradiction, right? Because they've shown here S is not in the centralizer. So no other element of the group D8 is in the centralizer, so it's precisely A itself. Right? You can just write the proof no, structurize the proof on your own. So this claim is obvious. What can I say about the other part? Now to show that, we know that the structure of D8 is of this form, right? Rs, such that R cubed is 1, S squared is 1, Rs is equals to SR inverse. So typically speaking, if I just show that the element R and the element S is in the centralizer of A, sorry, the normalizer of A in G, then precisely the whole group must be in the normalizer of A in G, right? Because the whole group is generated by these two elements. So if the generator of these two, so if the generator itself is in the normalizer, then any finite product of these elements will also be in the normalizer, right? So let's check. Okay. First thing first, we know that the powers of R will obviously be in the normalizer. That's quite obvious because they indeed commute. A is obviously in the normalizer of A, right? What about S? Okay. So what is SAS inverse? Okay. What is one S inverse? So it's precisely 1. What is SRS inverse? So we know that SR is equals to or let me just write it. RS is equals to SR inverse. What is the inverse of R in D8? It's R cubed because R cubed times R is R to the power 4. R to the power 4 is 1. I'm sorry here. This should be R to the power 4. R to the power 4 is 1. So the inverse of R in D8 is R to the power 4. Sorry, R cubed. Then so R goes to R cubed. Right? R square goes to R and R cubed indeed goes to R. Right? But this is precisely A, right? Indeed, this shows that S doesn't commute with elements in A because the set is the same as A, but its order is just changed, nothing else, right? So it's precisely A. So this means S is in the normalizer. Now, if S is in the normalizer, R is indeed in the normalizer because A is contained in the normalizer. So the generators of D8 are already in the normalizer. Hence, any finite product of them will also be in the normalizer. Any collection of elements which is generated by R and S will obviously be in the normalizer by the closure property, because we have indeed shown that it's a subgroup, or at least you guys have shown it's a subgroup. So this should be, in the normalizer, and this is nothing but D8. Normalizer by definition is contained in D8. D8 is contained in normalizer, so it's a both-sided equation. So it must be equal, right? What should be the center of D8? What should be the center of D8? First thing first, the center of D8 must be contained in the centralizer, right? Centralizer is A. I shouldn't use the term D8. Yeah, okay. Let's talk about D8. Yeah, correct. Let's talk about D8. So, the centralizer, the center of D8 is contained in the centralizer of any subset in D8, right? Here we're talking about the subset A. Let's be precisely A. So if the centralizer, if the center is indeed inside the centralizer of A in G, G is D8, then the center must have at least the elements 1 R square R cube, nothing else, right? Sorry, at most the elements 1 R square R cube. It's quite obvious to observe that R and R cube doesn't commute with the other elements of D8, with the elements consisting of S, right? And that's precisely from here. The only elements you will feel to commute or you will see to commute is 1, which is obvious, and r squared, because the inverse of r squared is r squared, because r to the power 4 is 1 and r to the power 4 is r2 dot r2. It's quite obvious. Okay. So so that typically implies that z d8 is nothing but 1 and r squared. Clear? I guess it's clear. Okay. Okay. This lecture, I want to make this lecture a bit long because I will end this lecture with a very simple observation. Uh, so this you can consider as example 3. So this observation is about the centralizer and normalizer in the permutation group. Okay. Let A be, let G be S3, and let A be the set 1 and 1, 2. Okay. And our claim is that the centralizer of A in G and the normalizer of A in G are both A. Okay, clear? Okay. So first thing first, A should be in the centralizer, right? Because you have only two elements. 1, 2 will obviously commute with 1, 2. There's nothing, very complicated in that. So A is indeed in the centralizer of A in S3. Now recall what Lagrange's theorem say. I am not proving it right here. We will. I guess I have proved the Lagrange's theorem in one of my previous lectures in the playlist. I will obviously consider that in some other lecture, the proof of it. But the Lagrange's theorem specifically says that the Lagrange's theorem. So it specifically says that if G is a group and H is a subgroup of G, then the order of H divides the order of G, considering both to be finite. Okay. In the case of infinite, there's nothing, yeah, it so order of G, right? Order of G. Okay. So now, so centralizer of A in S3 is a subgroup of G. Okay. Now A, in this case, you will carefully observe that A indeed is not just a subset; it's a subgroup. Okay. You could have observed it in the previous part also, whether it forms a subgroup or a or simply a subset. It forms a subgroup in this case. You can check it out in the example of D8. So order of A should divide the order of the centralizer of in S3, right? Moreover, the centralizer itself is a subgroup of S3, so it must divide the order of S3. What is the order of S3? It's 6, right? It's 3 factorial, it's 6. So if the order of A divides, now order of A is 2, okay. So order of A divides the centralizer of A in S3, and the centralizer of A divides 6, then what are the possibilities for the order of CS3? So you can observe that the order of A in CS3 in S3 is either 2 or 6, right? But obviously it cannot be 6. This, the order of A centralizer of A in S3, that cannot be 6, as the element 1, 2, 3, the element 1, 2 does not commute with the element 1, 2, 3. So precisely the centralizer cannot be the whole of S3. That is, typically speaking, the S3 is not abelian. S3 is not abelian. So what are the only possibility left? It must be 2. So this must be precisely 2. But if it is 2, then it should be the order of A, right? So this means CS3 must be precisely equal to A, as A is contained in CS3. I guess it's clear. I guess it's clear. Okay. Showing the normalizer of A in S3 is it's also very easy. So if I consider an element sigma in this, then it's if and only if you know, sigma 1 sigma inverse and sigma 1 2 sigma inverse, this is equals to it, that is one, sigma 1 2, right? So that means sigma 1 2 sigma inverse, this should be equal to 1 2, right? But this happens if and only if sigma is in CS3, right? So CS3A is E. Now again we argue that same thing, that A is obviously contained in the normalizer, right? Because every element will commute with its powers. So A is contained in this, that's one-sided inclusion. This comes here, so it's another inclusion, and so they are equal, right? Now, what should be the center of S3? Now, obviously, the center must be in the centralizer of any subset in S3. The centralizer of A, if when A is 1 and 1, 2 is A. Therefore, the center of S3 can be 1 and 1, 2 or something less than that. 1 2 doesn't commute with 1 2 3, so it cannot be in the centralizer, so this so cannot be in the center. The center is precisely the only the identity element. Is it clear? So we end this lecture here only. In the next lecture we will introduce the concepts of stabilizers and kernels of group action.